Hello everyone, my name is Mike Alden and I'm a PhD student here at Clemson University studying the flowering responses of cannabis with Dr. Jim Faust. Today, I'm very excited to present my research on pre-harvest fertilizer restriction, otherwise known as flushing. So back when I started my PhD in 2020, truthfully I had no idea what flushing was. My master's research was all on temperature and photoperiod effects with poinsettias, and that's kind of what we started looking at initially with cannabis. And that was, of course, until one day Allison came in for a visit and had a suggestion. Now, for those of us in the CRC, of course, all of us know Allison. But for those of you that are watching this video independently of the CRC, hopefully at some point in the future. Now, this person right here is Dr. Allison Justice. She obtained her PhD back in 2014 from Clemson University, also with Dr. Jim Faust, and since then has basically become the face of cannabis research. Now, I would strongly recommend for anybody that hasn't already read this article right here, White Ash versus Black Ash, to stop this video and go ahead and read that. Allison published that with Dr. Marcus Roggen in Cannabis Business Times back in August. And in this article, they cover just about everything you need to know about the context of flushing. And so to really understand the big picture of what I'm going to discuss today, this article Allison published is absolutely necessary to understand with this. So getting back to the original topic, flushing. What the heck is it? Well, over the years that I've been in this PhD program, I've had to familiarize myself with all sorts of new terms. And whenever there is terms that I'm unfamiliar with or trying to gain some context with, one thing I love to do is head over to old Ed Rosenthal's website. Ed's published probably a million different books on everything possibly related to cannabis. And on his website, he's got all sorts of information available. And on one of those pages on his website, he has a whole article on flushing. And so, of course, these are non-scientific sources, but if you want to gain the just context of the idea, some of these things are useful. And so on his website, he lists this quote, part of the flushing page, that there are a multitude of flushing methods, but they share a common goal: to remove most of the nutrients available to the roots, thereby encouraging the plant to use the non-assimilated salts and nutrients still remaining in the plant. And this is a quick demonstration just to show how we actually flush our plants. And all we're doing is passing tap water through the growing media continuously until we deliver about 15 to 20 liters of tap water. And so now that we know what flushing is, we can ask why it is. Why is flushing a thing? Why do cannabis plants get flushed? Why is cannabis really the only crop that gets flushed? And the why is, of course, related to the smokability of these dried flowers. Right from Allison's article, she says that the theory is that this ultimately yields a better smoking flower. And this is what the majority of cannabis growers believe. In one capacity or another, almost all growers flush. And, I don't know that there's any data to support this practice, but one way or another, all these growers are doing it. And, the idea of improving the smokability of your flowers is obviously important. I don't know that flushing is necessarily the thing that's doing it, but it does give us a hypothesis test. Now, unfortunately, we are not doing the type of evaluation that we see in the photo with Ed and Snoop, largely because we don't smoke any of the flowers, and we know better than to go asking the university for permission to have undergraduate taste testing trials. We're happy conducting physiology experiments, and that's what we'll be showing today and focusing on. How does flushing affect growth and development? These other things with the whys and the hows and the intricacies of the smoking quality of the flower, we're really not going to get into that because that's a very complicated issue. We will show how does flushing affect growth. Now, before we get into the actual flushing experiment, there's some other things I want to discuss related to cannabis production and kind of the value of cannabis products in general. And so this is a study by Steve Davenport looking at the Washington recreational market. And what we're looking at here on the x-axis is time, basically from when cannabis was legalized in Washington state, going from October 2014 to October 2017. And on the y-axis, we have percent of sales, right? So what percent of the sales were these different products that we're seeing here on the right? And so, of course, early on, in the early phases of this market, predominantly all the products being sold are dried flowers. But as time goes on, we actually see decrease in these dried flowers being sold and an increase or an expansion of these concentrates, of these extracted products. And so this figure is also from Davenport's study. And this is a slightly different time interval on the x-axis going from January 15 to January 18. And on the y-axis, we have dollars per 10 milligrams THC. And so what this really means is, as a retailer, when you sell 10 milligrams of THC, what product are you selling it as, which is what we're seeing here are these different trend lines. These are the different products, and these are the different values associated with this. And so the bottom line here is when you are selling, as a grower, when you are selling your THC that you've grown from your cannabis plants and one way or another packaged it as a concentrate or dried flowers or however, when you sell your THC as dried flowers, you are taking a discount. You are selling THC in the least valuable form. And that's really interesting to me. To compare that with concentrates, these cartridges, this is the most valuable, right? And so it's a reverse perspective for consumers, right? The best bang for your buck, of course, is buying these dried flowers. And actually the worst bang for your buck would actually be going to these concentrates. But these concentrates, these extracted products are what's gaining so much popularity. And so Davenport's study really shows nicely that we have really two main products that we can sell from our cannabis plants. One being our intact dried inflorescences, of course, and these are our flower buds. And these have a very high emphasis on qualitative characteristics, right? Compactness, the density, the aroma, the color, the taste, the touch of these flower buds. However, quantifying these parameters are very challenging and costly. Right, so something like measuring aroma. The first thing you think of is, well, let's measure the terpenes. Of course, how are you measuring terpenes, right? Are you measuring the volatilized terpenes in the headspace of a container? Are you extracting terpenes from grinded flower tissue? These will give you very different answers. And so to demonstrate some of the challenges, even with just measuring terpenes specifically, we'd like to show a couple of figures from our previous post-harvest studies. And I'd like to shout out Dr. Nishant Ariel and Elizabeth Leonard from the Multi-User Analytical Lab here at Clemson. They did the actual analyses for us, and they have made our job very easy for as far as taking the results and being able to communicate them to you guys. And so what we're looking at here is this type of analysis is called solid phase microextraction, or SPME for short. And this is a measurement of the terpenes in the headspace of a container. And so what we see on the x-axis here are the different detectable terpenes that were in this study. And on the y-axis, we have linalool D3 equivalents. And so linalool is used as an internal standard. And so the concentration of these different terpenes is relative to the abundance, or relative to the internal standard. And so we see the usual agents responsible for a lot of the aroma or the fragrance in cannabis, right? Alpha humulene, beta caryophyllene, linalool. These are, we would expect to see these in pretty high concentrations, but just take mental note of the y-axis here going from 0 to 400. Now let's compare that to hexane extraction with those same flower buds treated exactly the same way, and now we get a very different figure, right? If we look at these, one thing that jumps out is that the most dominant terpene here is guaiol. This is one that was almost non-existent in the headspace, and now if we look at the actual flower tissue, it is clearly the most abundant. And the other thing that probably jumps out to you is the y-axis here. The previous figure went from about 0 to 400. This is going from 0 to 25,000, right? And so we see a very different scale of how abundant these terpenes are depending on where you're measuring them. And so what this figure is just combining the last two figures and overlaying them on top of each other. And so we can kind of directly compare the relative abundance of these terpenes in the headspace and in the flower tissue. And so clearly just measuring this absolute terpene content in the gas and tissue doesn't really tell us much, right? We have much higher concentrations in the flower tissue than in the headspace, and there are different terpenes dominant depending on where the measurement occurs. But truthfully, these type of analyses cost several $1,000s, right? These are very expensive types of experiments. I think it takes a dedicated funding source with a very clear idea where they're trying to go with this type of project, right? This was fairly exploratory for us and gave us some good background, but these are the type of things that we don't really have answers for, so we're not going to continue discussing them. So our second class of products then are extracts and concentrated products, otherwise known as concentrates. And these have an emphasis on yield of specific cannabinoids. For these types of products, we do not care about the qualitative aspects at all. All we want is more yield. And why we only care about yield is highlighted really nicely in this diagram by Song et al. Back in 2022. They did a really nice review of the different extraction methods available for cannabis. And what they're showing here right at the beginning of this diagram is that it starts with the receiving and separating their dry biomass. And that dry biomass is just separated into flower, leaves, and hash. Right? The density or compactness of your flower buds didn't matter at this stage. And so this opens up the idea of maybe altering some of our cultivation strategies to improve some things. Which all of this leads to the main idea of my entire PhD project, being that cultivation strategies that improve yield can be incompatible with those strategies that improve qualitative characteristics. And we've already demonstrated this to some degree with our photoperiod research. We have shown that there are different optimum photoperiods for different cultivars depending on your final desired product. And so this slide is from my CRC talk back in August on my photoperiod research. And so what we're looking at here on the x-axis are the different photoperiods that we provided in this study from 10 to 14 hours. We have our three cultivars, Sunset, OG, and Tiger. And on our y-axis, we have yield of CBD. And so we measure this by we calculate this by measuring the flower bud dry weight from each plant. We multiply that by the CBD percentage, and then we are able to calculate our yield of CBD. Okay. And so what we see here, specifically just looking at OG, is that we see a trend where as you increase photoperiod from 10 hours up to 12 hours, you are increasing your yield of CBD. However, if you extend that photoperiod past 12 hours to 13 hours, you have now decreased your yield of CBD. And so when it comes to extraction, clearly the 12-hour photoperiod would be the best photoperiod to provide. You would never provide something else because you're always decreasing your yield by providing any other photoperiod. Right? However, maybe that's a little more complicated when you consider the actual dried inflorescence, the actual quality of these flower buds. So these are the terminal inflorescences of OG from this photoperiod study. And so, looking at this 10-hour photoperiod specifically, we see that these flowers are very well formed, that these are well-developed flowers. The stigmas are largely orange and brown here, right? And if we compare that to the 12-hour photoperiod, well, these flowers are less compact or less filled in. The stigmas are predominantly white, which would suggest a less mature flower. And so some of these things are really interesting to think about, right? Because qualitatively, the 10-hour photoperiod looks significantly better here than the 12-hour photoperiod. But if we're only concerned with extraction, well, then you would never provide a 10-hour photoperiod because it doesn't matter what your flowers look like. And so the last thing I want to discuss before we actually get into our flushing data are these two studies, which, as far as I'm aware, are the only studies that have been conducted on flushing. Now, Stemmeroff's flushing experiments were part of his master's manuscript, and the Wedrick study was conducted by a private company. So I'm always skeptical of those types of studies, but at least we have something to look at and otherwise think about. Now, Stemmeroff's research, the long and the short of it was basically this quote here, is that flushing was found to be ineffective in removing any significant amount of nutrients from the bud. And that is one of the central ideas with flushing, is that somehow you are removing the nutrients from the growing media, right? Which you can do that fairly easily, with the idea that you're forcing the plants to use those non-assimilated salts and things, as Ed was alluding to. But right here, we have a study that's saying it didn't matter, that flushing didn't have an effect on these nutrient concentrations in the flower. And so this quote is also from the Wedrick study, and that overall there were no significant differences between treatments for flower weight, THC, or terpene content. And so, this is really interesting to me. So we have one study that's saying that, the flowers were, the nutrient content of the flowers was not affected. And also they really didn't see any differences with the flower dry weight. 2 years later, a different study is done and they found no differences in the flower weight, THC, or the terpene content of their flowers. And so, to date, there are only these two studies that have been done, and both of them are saying, no, that these ideas that what we do with flushing, they don't really add up to what we're observing. Now, of course, there's plenty of other things that are involved with, I guess, the quality of the flowers and what makes a flower more smokable. But for the things that we can readily measure fairly easily, flower weight, cannabinoid content, nutritional content, flushing is not really doing much of anything, at least as far as these studies are concerned. So now I think we're finally ready to talk about the experiments that we have done here at Clemson. And so we have done 4 flushing experiments, but we're predominantly going to show you the data from the 4th experiment, because this is the one, as we do these experiments, we get better and better and more familiar with how to do them and things to look for and measurements to make. And so this 4th experiment, we replicated twice. They were temporally separated by about 3 weeks, and they were done exactly the same way. So we have 2 complete sets of this experiment. And so the main idea here is that we basically took 50 plants of OG that were flowered under a 12-hour photoperiod for up to 8 weeks. All plants were finished with 16 shoots per plant, and each shoot was terminated by an inflorescence. Now, just to show you what our plants look like during our experiments, basically what we do is we pinch our plants 4 times to get to 16 shoots. And how we do this is basically when we transplant our cuttings into our 1-gallon containers, we pinch back to 2 nodes, and each time we pinch after that, we leave 2 nodes behind. So 2 to 4 to 8 to 16 shoots finally on the last pinch. And what's interesting is that we pinch at the start of short days, and we pinch 1 week after starting short days, which I think for a variety of reasons is extremely helpful for keeping plants compact and getting much more uniform flowers. But that'll be more on the topic of next month's CRC video. But for now, what I want everyone to, I guess, see or appreciate is basically all these plants look the same up until the flushing treatments. Each of these plants has 16 inflorescences, which is basically what we do is just cut each of these 16 shoots, and then we can separate that pretty easily from the rest of the vegetative mass that's down here. And so just to make sure we're on the same page, we like to show basically how we harvest our plants. And so this picture on the left is that same plant from the photo. And what we do to harvest the whole plant is we just cut it right above the soil line, which is what you can see here. We snip that right above the soil line. And so we weigh this whole thing, and this is our total fresh weight. Now we remove these 16 inflorescences from the plant, and then that leaves us with our vegetative fresh weight. And so here are the 16 inflorescences that were separated from the vegetative mass for that plant that we harvested. And so what each of these are basically what has developed following the final pinch. And so we pinch at the start of short days, and we pinch one more time after that. And so this is a collection. These 16 shoots right here are basically what grew following that final pinch. And so basically all of our floral matter is right here. This is completely separate from what we would consider the vegetative mass, although of course there are leaves and bracts in here. These these developed only under short day conditions, and this is what we're defining as our inflorescence. And so this flushing experiment is really divided into 2 groups. The first group being our growth over time experiment. And so the main idea from this is that among these 50 plants that we had for this whole experiment, 25 of those plants we separated into one group, and basically 5 plants from that whole group were randomly selected each week from weeks 4 through 8, and they were destructively harvested and data were collected. We collected the fresh weight, the dry weight, and we took samples from the inflorescences for cannabinoid and nutrition. Now, these plants were provided fertilizer the whole time. They were just basically treated as if plants that were just keeping healthy in the greenhouse for several weeks, and this was allowing us to track growth over time. The second experiment was, of course, our flushing experiment. So we really wanted to pair both of these together because we wanted to see, one, how is the plant growing week to week under normal fertilizer conditions? And 2, how does terminating fertilizer application during the growth affect overall growth and yield? And so we're going to go ahead and take a look at the data from this first experiment, growth over time. And so in this figure, we're looking at our dry weight data. And so on our x-axis, we have weeks of short day going from 4 to 8. And on our y-axis, we have our dry weight, being our vegetative, inflorescence, or total dry weight. And so 2 things really jump out here. Number 1 being that from weeks 4 through 8, our vegetative dry weight is completely flat. Right? We don't have any changes in our vegetative dry weight, which tells you that during our experiments, all of our growth occurs in this inflorescence, right? All of our changes are happening here, right? And so from weeks 4 through 8, our increase in inflorescence dry weight is linear. So looking at this figure, it seems fairly obvious that flushing during this time would decrease yield. You are terminating fertilizer application while these plants are still growing each week. And so here's our CBD percent data. And so it's the same x-axis going from weeks 4 through 8 of short days. And on our y-axis, we have CBD as a percent dry weight of the flowers. And so going from weeks 4 to 5 to 6, we're getting linear increases with each week. However, from weeks 6 to 7 to 8, this is just flat. And so this would suggest that we have reached maybe a physiological maturity or a chemical maturity of the product, where each additional week of short days no longer leads to a significant increase in CBD content. And so I just wanted to put these 2 figures side by side here. And so on the top figure, we're again looking at our inflorescence dry weight. And on this bottom figure here, we're looking at our CBD percentage. And so, we can really see here that we have two independent parameters that need to be tracked when you're considering growth over time, and that these two parameters can help you determine your optimal harvest time. Now, looking at these figures too, we wouldn't expect from this inflorescence growth to just continue linearly indefinitely forever. Obviously, this would eventually flatten out, kind of like we're seeing here with the CBD percent. Although the CBD percent, what would be interesting is that I think as you go past week 8, we know that the CBD will not stay in that form forever, and it's going to degrade into additional byproducts. And so, going past week 8, we're probably actually going to see the CBD percentage begin to decrease as you go to week 9, 10, and 11. And so this figure is a calculation of our yield of CBD based on our inflorescence dry weight multiplied by the percent CBD. And so this calculation allows you to readily identify your optimal harvest time, as deciding when to harvest is a major cultivation challenge. We can define our optimal harvest time for extraction as the minimum number of short days necessary to reach a maximum yield, meaning that any further increase in short days does not lead to a significant increase in yield of CBD. Every day spent growing correlates to more and more resources invested in obtaining your end product. So of course we want to minimize this to increase our number of crop cycles per year. So looking at this figure, we would always at least go out to week 8 when we're looking, when we're trying to identify our perfect time for harvest for extraction. But if this were to flatten out at week 9 and 10, well, then there wouldn't be any reason to go to grow your plants past week 8. Now, there may be qualitative considerations for going past week 8, but that's a completely separate argument from trying to identify your optimal harvest time for extraction. And so as I record this video, we have an additional rep of this experiment going in the greenhouse where we extend this experiment out to week 10. And so hopefully we're able to identify our optimal harvest time specifically with OG coming up. So here are some of our macronutrient data from this experiment. We still have the same x-axis going from 4 to 8 weeks of short days, but on our y-axis we have our various macronutrients as a percent dry weight of the flower tissue. And so what we're seeing here is nitrogen, potassium, calcium, and phosphorus. Now we have all of the essential elements analyzed for this experiment, but these were kind of the ones I wanted to just highlight really quickly. And so what we see here, especially with nitrogen and potassium, that these are relatively flat, so we're not getting much accumulation in those inflorescences from weeks 4 to 8. However, what we see with calcium is that we actually see a decrease in the calcium content as we go from week 4 to 8. Which is interesting because from my experience, as you allow cannabis to grow longer and longer, it gets more and more susceptible to botrytis, which this may be related to that. And compare that to phosphorus, where actually phosphorus is accumulating in the flower tissue as you increase from weeks 4 through 8. And so I just wanted to zoom in on this phosphorus trend specifically. Now, Mitch Westmoreland and Bruce Budby at Utah State are doing some excellent studies with phosphorus, and they have put forth a hypothesis that cannabis will cannibalize itself to maximize phosphorus content in the flowers during short days. And the idea is to accumulate as much phytic acid in the flowers in order to basically provide an energy source for the seeds. Now, of course, we keep our plants unpollinated, so that accumulation of phosphorus is almost pointless for the plant, but it makes sense on a physiological basis why this is occurring. So I just wanted to quickly go through the conclusions that we can draw from our growth over time study. First, being that flower dry weight and CBD percent are essential parameters to track when attempting to identify your optimal harvest time. I don't think growers should be trying to define this as some proportion of orange stigmas around the terminal or the color of the trichomes and all that kind of jazz. I think what's much simpler is just to track your flower dry weight and your CBD percent on a weekly basis, and that'll tell you everything you need to know. Number 2, our optimal harvest time is defined as the minimum number of short day photoperiods necessary to reach a near maximum yield. Of course, there may be reasons to go past that optimal harvest time for qualitative considerations, but when we're thinking about extraction, we want the fewest number of days per crop cycle, so that way we can get more crops per year. Number 3 is our optimal harvest time will vary considerably among cultivars. And so, of course, that these varieties need to be evaluated separately, which I understand can be very challenging for those cultivators that have dozens of different varieties. But truthfully, that's more of a you problem. right? I think in general that growers need to be simplifying the amount of varieties that they're growing so that you can grow these varieties very well. I don't think it makes sense to just grow all these different varieties if it's not done with precision. And number four being that the accumulation of phosphorus in flowers each week seems to be a redundant physiological function in the context of cannabis cultivation, right? We keep our plants unpollinated, but these plants are accumulating all this phosphorus in anticipation of being pollinated. Okay, so that was our growth over time experiment. And so now we're going to take a look at our flushing experiment. And so our flushing experiment was pretty simple as well. What we did was we flowered all of our plants for 8 weeks. However, each of the flushing treatments were flushed for some duration prior to harvest. So we have harvest at week 8, and plants were flushed for either 0, 1, 2, 3, or 4 weeks prior to harvest. Okay, and so how we did our flushing treatments was pretty simple as well. All we did was basically take drip emitters, and we're passing tap water, or we're feeding tap water into the top of the growing media. That tap water is passing through the media and leaching out the bottom. Well, we continuously feed tap water through the growing media until about 15 to 20 liters has been delivered, and then we allow our plants to settle for about 30 minutes to an hour. After that time, we'll take a small volume of water, about 100 milliliters, pass it through the top of the media, and measure the leachate that comes out. If the leachate EC is less than 0.2, well, then we know that we have a flushed plant, or not necessarily a flushed plant, but the growing media has been flushed. That there is, we have pretty much removed most of the nutrients available to the plant. So here's just a diagram or a schematic of how we actually did our treatments. And so what we're seeing here on the top is our short day photoperiods in weeks, going from 0 is basically just the start of short days, and up to week 8, which would be day 56. And then here we have our flushing duration in weeks, going from 0 down to 4, 0 being our control. And so what you're seeing here is basically that the control would get fertilizer the entire time up until harvest. The 1 week flushing treatment would get fertilizer all the way up till week 7. On week 7, the growing media is flushed, and then every irrigation event thereafter that the plant needs is only tap water. Same thing with week 2. Starting on week 6, the growing media is flushed, and then the plants are provided only tap water until harvest. Okay? And so this is how our flushing treatments are done. And so this is a overhead view of basically what these plants looked like on week 8, and these are the different flush durations going from 0 to 4. Now, what's pretty interesting here is that, of course, the control is pretty much all green here, but you do see some pretty quick yellowing or chlorosis of the leaves occurring at even just a 1 week flush, and you see the severity of this increase pretty drastically going from week 2 to 3 to 4. Although, if you really look at weeks 3 and 4, you're probably not seeing too much difference between these. And so what's actually different about these is that you need to see them from the side, because most of those bottom leaves, those lower leaves on the week 4 treatment, are completely gone. Those leaves are, they have mobilized everything they possibly could have out of those leaves and have since abscised. So this week 3 treatment would have a bit more leaf material underneath the canopy, versus week 4, this is it. There is basically nothing underneath here. And of course, like the week 0, the control would have a maximum amount of foliage underneath. And so, ideally, that could also be a method of, removing leaves early on to help facilitate easier harvest. That could be a benefit of flushing, is that you're forcing the plant to abscise leaves that you would otherwise have to have labor manually remove. So there's one thing to consider there. And so here's just a closer look at the individual flowers from those plants that we were just looking at. And so, you can see these nutrient deficiencies a little bit better up close, and you can see how they are affecting the bracts right around these inflorescences. And so both things are pretty interesting. You can visually see that these flushing treatments were having an effect on the, at least the nutritional status of the plant. So let's take a look at our flushing data. On our x-axis here, we have flush duration going from 0 to 4 weeks. And of course, our 0 is our control. And on our y-axis, we have dry weight for vegetative, inflorescence, and total. Now, as you can see with the vegetative dry weight, that this is effectively just a flat line. There is a slight downward trend here, but not nearly as much as we're seeing with the inflorescence and the total. Now, these trends are exactly the same between the two of these, but I just showed the letters up here that are indicating the significance between treatments. I just showed on the stop line for clarity. And so what we're seeing here is that the control and the 1 week flush are not any different from each other. However, if you extend that flush out to a 2-week flush, now you have significantly lowered your inflorescence dry weight on a per plant basis. And we see that the 2 and 3 week weren't any different from each other, but the 4-week flush was different from all other treatments. And so as we saw before, our inflorescences are really kind of a mix of flower buds and trim. And so we actually break these down further, and so we'll look at that here in a second. And so here's a photo just to show how we break down our inflorescences into flower buds and trim. And so as you can see here on the right, that what we consider the trim is mostly comprised of internodes and bracts. And so what we're left with are the flower buds from those inflorescences. Ultimately, these flower buds are what we sample for cannabinoid and nutrition analysis. And so we still have the same x-axis here, the flush duration going from 0 to 4 weeks. And on our y-axis now we have those flower buds and trim. And so what we can see pretty readily here is that as the flushing duration increases, our flower bud dry weight continues to decrease. The flower bud dry weight was significantly greater in the control than it was in the 2, 3, and 4 week treatments. And so from this experiment, we can say pretty confidently that at least with OG, that if we flush for more than 2 weeks or more, then we're going to lead to a significant decrease in yield. And, I think that makes sense. We're cutting off fertilizer application while these plants were still growing in that linear phase. They didn't start to saturate at all. And so if we're cutting off fertilizer during that linear growth phase, then of course we're going to see negative or adverse effects on our yields and our flower buds. And so what we have here is a collection of the 4 flushing experiments that we've done. Now we've only looked at the fall 22 experiments today, but as you can see with the other 3 experiments, at least for the effects on flower dry weight, that the trends are all saying the same thing, right? That as flushing duration increases, our flower dry weight decreases. Now, as we saw earlier in our growth over time experiment, OG was still growing linearly from weeks 4 through 8, where these flushing treatments would have been applied. I think there's some possibility that if a cultivar stops linear growth prior to week 8, then flushing would not have nearly as much of an effect, right? The plant was mostly finished developing by the time you start flushing, so there's not much to be lost by cutting off fertilizer early on. So if we think about this figure through the lens of extraction, of course, flushing can be a detrimental cultivation practice, as this tends to decrease yield, and when it comes to extraction, we don't ever want to be decreasing yield. However, if we think about a 1-week flush, which typically isn't any different than our control, well, why wouldn't you flush, right? Why would you continue applying fertilizer if it's not leading to any additional growth or yield? There's an obvious cost savings benefit here, right? Each fertilizer application skipped decreases the cost of your inputs per crop cycle, especially if you are using those expensive pre-mixed fertilizer solutions or bloom boosters. You multiply that by the number of crops you grow per year, and if you're a multi-state operation, then by the number of facilities in your organization, the savings add up very quickly. And it's completely free. Nothing to install or change, just a simple switch to clear water for some number of days to help keep money in your pocket. But you need to first identify what range that you can flush for without affecting your yields. Now, to compare that with the flower buds, I think there's a few things to consider here, more than just the yield like we do with extraction. Perhaps a decrease in yield is acceptable because something else about the flowers has been improved, right? So for example, we saw that the nutrient deficiencies actually bring out a really nice palette of colors in these inflorescences, whereas the control is largely just a mix of green and orange. Both, of course, of these are valuable for their own reason, but perhaps modifying the colors of your inflorescence is something that's useful. Another example may be that, as I mentioned earlier, that the 4-week flush leads to drastic leaf abscission below the inflorescences. The inflorescences themselves are much smaller, which may lead to easier handling and processing as these things are broken down into buds and trim. Perhaps these smaller flower buds are more compact or more dense. And then if you consider maybe using a mixed approach, using OG here as an example, where we finish half our crop with a 1-week flush, whereas the other half of the crop is finished with a 4-week flush. Now you have a really nice mix of these large, full, consistent flower buds, as well as a mix of these smaller, denser, and very colorful flower buds. And these are the types of things that we need to be thinking about as growers. We need to be focused on identifying more methods to optimize the growth of our plants for the products that we desire. And so I just wanted to reiterate with our dried flower buds that this is what we sample from for our cannabinoids and nutrition. What we do is we try to fit on a per plant basis. What we try to do is fit as much of the flower buds into our coffee grinder. We grind all of that up until it's a nice homogenized powder, and then we scoop out 2 to 3 grams from that and package that up and send it off. And so once again, we have our flush duration on our x-axis, and now on our y-axis, we have our CBD percent, a percentage dry weight of our flowers. And so what's pretty interesting here is that we actually have our lowest CBD percent in the control, although it wasn't significantly different than the 2 and 3 week flush, but we do see a general trend here, right? The longer that we flush, the trend seems to be increasing. And at first glance, you might think, well, the longer flushing durations here are helping additional synthesis of CBD, which I don't necessarily think that's true. I think what we're looking at here is actually a dilution effect, right? In the control, we had our largest flowers, and so when we sample from those on a per gram basis, we would have the least concentrated CBD percent here, right? The most diluted flowers. However, as we increase our flushing duration, our flowers are getting smaller and smaller. And so if we think about this 4-week flush, which had the smallest flower buds, and now it also has the highest CBD percent, I think what's going on here is that we just have a smaller volume that we're sampling from, and so it's more concentrated on a per gram basis. Now, to follow up on that last slide, what I wanted to show is the CBD trends for the 4 experiments that we've done with flushing. And as you can see, we have, at least 3 different trend lines here. And so, if we look at the spring 21 experiment, what we're looking at here is basically going from 0, 10 to 20. We see a really sharp increase as you increase your flushing duration. You also get a pretty rapid increase in CBD. But then going from 10 to 20, really not much difference here. Compare that to experiment 2, where we get this kind of just gradual decrease in CBD. And then, the third experiment, where it's kind of the same as the spring 21 experiment, but this is just more of a gradual increase up until you get kind of a bigger jump here. And then, with our most recent experiment, this is the one we're most confident in, we get this kind of, S-shaped or sigmoid trend almost. And, you really have to stop and ask yourself, does this matter? Seriously, do these CBD percentage numbers actually matter? Can a customer tell the difference? Maybe not so much with CBD, but with THC, can a customer tell the difference between 20% THC that's in the flower buds or 21%? It's an arms race between different cultivators because they all want to outcompete each other, and you have consumers are basically only shopping based on how high the THC content is. And I don't know, the arms race here, it doesn't seem like it makes sense to me. I think there are, many other factors at play that would correlate better with the smoking quality of the product. And as far as measuring THC and CBD, it's useful, especially for extraction. This is extremely useful. But when we're talking about flushing and how does flushing affect cannabinoids and these things, I don't know that it matters. We don't have anything consistent across our experiments. We can say between this one experiment we have 2 consistent reps. They both looked like this, but we do this experiment at different times of the years in slightly different ways, and we get very different results. Now, what I wanted to show here on this slide is basically just the relationship that we've observed between flower dry weight and yield of CBD. And yield of CBD is, of course, calculated by multiplying your flower dry weight times your CBD percentage. And so, this is really interesting to me because what you're seeing here is the long and the short of it with, as far as extraction is concerned, that if you want to maximize your yield of CBD, well, then you need to produce as much flower dry weight as possible. And to do that, you would never flush because, as we've seen, flushing will decrease your yield at some point. Now, what is a good an alternate idea here is that, well, as we saw, that the 7-day flush or the 1-week flush didn't lead to a significant decrease in yield. Well, in that thought, if you're using, especially some expensive fertilizers, pre-made solutions, bloom boosters, and all those things, 1 week of eliminating fertilizer, may lead to significant economic savings. So, you're not decreasing your yield at all, but now you've cut off a week of fertilizer. Now you multiply that by how many crops you produce per year. If you're a multi-state operation, multiply that across the facilities and the savings add up. But you have to first consider measuring, basically how does the flower dry weight accumulate each week, where is your optimal harvest time, and if you flushed for 1 week, was it any different? Did you decrease any of your yield? And if you did, well, maybe you could just scale that back to 3 days. And if maybe 7 days didn't do anything, well, maybe try 10 days, maybe try to cut off a week and a half of your fertilizer. Those are the only contexts I could see where flushing makes sense. And it wouldn't be flushing in the way that we have done for this experiment. It would just be, switching over from tap water. And so the idea with flushing would be more so that you would be reducing the amount of fertilizer you apply to the crop overall, but not for the idea of somehow improving the quality of the flowers. And finally, we're going to show our nutrition data associated with our flushing experiments. So once again, we have our flushing duration, 0 to 4 weeks on our x-axis. And what we have here on our y-axis is basically the nutrient concentrations as a percentage of dry weight of the flowers. And so what we have here on the top line is nitrogen, this is potassium, calcium is this purple line, and phosphorus is this red line. And so what do we see? Well, we see that stemmer off was wrong, first of all. Flushing absolutely does change the nutrient content of the flowers. And what's really interesting too is that what we see is this opposite relationship, I guess, when you consider nitrogen and calcium or calcium and phosphorus. As nitrogen and phosphorus are both decreasing in the flower tissue as you increase your flushing duration, calcium is actually increasing, which there are some very interesting ideas surrounding that, or some possibilities with that. Now, I wanted to isolate calcium here and just talk about this for a second. This is really interesting to me because of the relationship of calcium with botrytis. And botrytis is, anybody that's watching this video has probably dealt with some of their plants getting botrytis, and it's just devastating. It's just terrible to see happen. You put in all that effort to get this beautiful plant, and then all of a sudden it just starts melting right in front of you. It's just terrible to watch. And, here in Clemson, we really struggle with botrytis during the summer, from June through mid-September. We really can't flower our plants past week 7. And last summer we tried, I think, 7, maybe 8 different types of products that are supposed to work on botrytis. And these are labeled for ornamental crops, but we wanted to trial it, and nothing worked. Now this graph, this figure is actually kind of interesting, because what we're seeing is we are actually pushing more calcium into those flower tissues with longer flushing durations. Now, this could be a little misleading because the flowers are smaller, of course, in the week 4 treatment, so we could be concentrating some calcium. But in theory, if these longer flushing durations could correlate with higher calcium amounts in the flowers, might therefore make it more tolerant or resistant to botrytis infection. That might be a major major finding, or some major potential here. It's for someone like me doing research here. If I could find a way to not have to cut my experiment short for 3 months out of the year, that'd be fantastic. I think there's a lot of other things to consider here, but this might be interesting. This might be promising, using flushing as a tool during the summer or other months where you're prone to botrytis, as a tool to help manage it. And so I just want to go through the conclusions that we can draw from flushing. Number 1 being that our findings do not agree with those of Stemmeroff or Wedrick. Not even close. We can clearly affect the nutrient content of the flowers, as well as the flower dry weight and cannabinoid concentrations. Number 2, flower bud dry weight will be negatively affected by flushing if the plants are growing linearly week to week. If you cut off fertilizer while those plants are still growing, of course you are going to negatively affect those flowers. However, this decrease in yield may be acceptable if something else about the flowers is improved. Now, number 3, in the context of extraction, flushing should be used only as a tool for cost savings to reduce inputs per crop cycle. And so that's all we have for today on flushing. Next month, we'll be talking about height control techniques, about how to keep your plants more compact, and especially those flowers. And then the following month, we will be talking about flushing with a different variety called Jack.